In section 10.3, we're looking at shape still, but now we're adding in lone pairs. So if we have a bond, we can kind of represent that bond between two nuclei here, one atom's nucleus and a center, and these electron orbitals and electrons that are sharing density between them. So that negativity in a bond, which would say be one of these lines in methane, that's what we're looking at here. So this would say be hydrogen, this would be carbon with the line between it, and compare that to these things with lone pairs. So it's the difference between, say, carbon to chlorine, carbon tetrachloride, and we have a bond, but the chlorine atom has this lone pair of electrons. One thing to notice right away is that this is more squished. It actually has a little bit more density towards closer to the nucleus than it does when it's stretched out a little bit between the two nuclei. So what happens to the geometry when we introduce these lone pairs? Well, let's just look at tetrahedral first. We can get a good idea of this. It's something like CH4, a Lewis structure that we've seen many times. We have no lone pairs. This is AB4, and it is tetrahedral. When we introduce a single lone pair, such as in the ammonia molecule, we have a slightly different shape. The lone pair still takes up a shape, so if we draw this out as a tetrahedron, we still have electron groups trying to get as far away from each other as possible. Okay. So these groups are still pushing, push, 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 push. So it's a tetrahedron shape overall, but these electrons on the top are not going to be what runs into other molecules. So we're going to ignore those electrons when it goes time to write up or talk about the shape, because what's going to actually crash one molecule into the next is going to be the nuclei, going to be the center of where those electrons are located at. So when we look to make the original electron geometry, we include all of the lone pairs and the atoms. So electron geometry, the atoms attached, so bonds, and lone pairs. Okay, so that gives us those shapes: linear, trigonal, planar, tetrahedral, trigonal, bipyramid, and octahedral that we talked about in the previous section. But now, when we have an AB3N arrangement, this is actually going to be named something slightly different. Okay. What this is going to be named is, see, we got the original tetrahedral geometry, but the lone pair pushes on this, and you end up with what's referred to as a trigonal pyramid. Okay. So, trigonal pyramid shape. Now, why was that angle decreasing? We saw in the original tetrahedron, we had 109.5 degrees, but we were saying in this ammonia molecule with a lone pair attached to it, we only had 107 degrees. Well, that's because of this kind of flattening out and increased density of the electron closer into the nucleus. When we have that lone pair above the nitrogen, we actually get more push on those other electrons and the bonds between the nitrogen and the hydrogen, and that kind of compresses and squishes farther down these particular bonds in the rest of the atom. Okay. Now if we have two lone pairs, like in water, we're looking at an AB2N2 molecule, and what we refer to this one as is just as a bent shape arrangement. Yeah, I know, highly scientific after all this tetrahedral and trigonal pyramid, etc. But yeah, this one's just referred to as bent. And the angle again is compressed. We have 104.5 degrees instead of the 109 or even the 107. Now we have two tetrahedral, now it looks like a bunny, I'm sorry, two tetrahedral lone pairs that are sticking out. Electron, electrons, electrons, and hydrogen, bond, electrons, and hydrogen. So these lone pair electrons in the tetrahedral electron geometry are pushing on those bonds to give us this decreased angle in the molecular geometry. Okay, so that's what we're showing here. So tetrahedral ideal 109.5, bent shape 104.5. I'm not going to ask you to memorize these individual angles for the geometries of the molecular geometries. You should know the electron geometry angles, these ideal ones, if everything is there and there are no non-bonding pair electrons. But the diminished angles that occur when you have some lone pairs or some N groups in the ABN designation, those you don't have to memorize. I just want you to know that they're smaller than if you had the ideal geometry. To make sure everybody's on the same page here, I want to just point this out, because I'm using these terms, I'm assuming you've read the book, but just in case. Electron geometry, A and B, no N groups. Okay? And that will be the base as well. That's the base configuration of whatever the molecule is, and that includes everything. So the molecular geometry that's going to be where we have A, B, and N, and we're going to give the name based only on the A's and B's. Now the thing to remember is the molecular geometry gives us the name. The electron geometry gives us the base shape. Okay? So water has an electron geometry. When we consider all the electrons, lone pairs, whatever else we have there, electron geometry of a tetrahedral. Okay, so lone pairs, hydrogens, that's its electron geometry, including everything there. And if we named the electron geometry, we'd say that's a tetrahedron, and that's how we set it up before we go in and we look at just the bonds to atoms. Okay? So when we name it, when we name the molecule, we name the molecule shape. Okay, so we're not just putting it together and drawing the shape. Drawing the shape comes from the electron geometry. But when we name the molecule, wow. When we name the molecule shape, then we don't look at the electrons. We don't change any of the angles. The angles stay the same because they are forced that way by the tetrahedral electron geometry. But when we name the molecular geometry and say that this molecule is bent, not a tetrahedron, that's because we're looking only then at the atoms and the angles involved between those atoms. Now, well, what if we have the electron geometry of a trigonal bipyramid? You know, a trigonal bipyramid has these 5 groups, and we can see an AB5 would have trigonal bipyramidal electron geometry and molecular geometry. So if something had 5 groups attached to it, you'd name it the same way, trigonal bipyramid. But what if it has extra electron lone pairs present? So sulfur tetrafluoride, for instance, has a Lewis dot structure that shows that there's 5 things on the center atom. 4 of those things are fluorine atoms, but 2 of those are, or one of those groupings is a lone pair of electrons. Well, we have 2 choices, right? We can take off the top and make kind of this trigonal pyramid shape, something like that, or we can take off one of the sides and make this other shape. Okay, so let's look at what we get. That's a lot of lines. If we take off the top of this trigonal bipyramid, now we have a 90-degree angle to 3 other sets of electrons in bonds, and this pushing of the lone pair is pretty strong compared to those, so interacting with 3 of them is not very favorable. If we take one off the side, which we refer to as the equatorial region, this region around the triangle, okay, trigonal bipyramidal shape, fluorine, fluorine, sulfur in the center, fluorines on the outside, now electrons here. Now we only have 2 90-degree close by fluorine electron bonds. Okay, so the push on those electrons in those bonds is going to be strong, so we want to minimize the amount of 90-degree angles that occur. So 3 90-degree angles versus 2 90-degree angles. 2 90-degree angles win out. And that's with a lone pair placement when we have only 1 non-bonding electron set. So AB4N. Okay, so we have 5 attachments, or 5 things, giving a trigonal bipyramid, whatever, electron geometry. And then we need to name this, and what we name this is actually seesaw. AB4N has a seesaw geometry. When we consider the molecular geometry. Okay. You can kind of see this as a seesaw if you kind of turn your head sideways and kind of tip this around. And you see this, and it kind of balances on these legs, and then these 2 things here are the teeter-totter that goes back and forth, etc. Okay, so seesaw geometry. Now if you take 2 groups off, same thing holds true. We want 90 degrees instead of 2 90-degree angles instead of 3, so we take this second lone pair for a molecule that would be AB3N2. So still 5 things attached, so still a trigonal bipyramidal electron geometry. But now the molecular geometry, where we only consider the atoms attached, is referred to as a T-shaped geometry. So electron geometry, what sets up the shape, pretend like you can't see the lone pairs, that's what we name the shape. So you can have the same sort of thing with 3 groups, but now our trigonal bipyramidal electron geometry leads to a linear molecular geometry, and this would be AB2N3. 2 more. If we have an octahedron, then we can have anything that has 6 attachments. The simplest version is the octahedral, AB6, but if we start replacing groups with lone pair electrons, such as in bromine or pentafluoride, we see that the electron comes off, and we're left with what is basically a square pyramid. Okay? So a square pyramid, there's no real consideration here for the first electron. No matter where we took this off, we'd end up with the same shape, because all the atoms around this are pretty much symmetric. It's all 90-degree angles. So tetrahedral, or not tetrahedral, I'm sorry, octahedral electron geometry, the AB5N shape adopts a square pyramidal geometry in the molecular geometry sense, where we name it. If we take off a second lone pair, that lone pair is going to want to be as far away from the other lone pair as possible, because those push on each other pretty hard, and what we're left with then is just the square. So if we have A, B, 4, and 2, we still have 6 things attached, but when we look at just the atoms, the A's to the B's, we end up with a molecular geometry of square planar. So we have 2 basic ways to look at this. We're looking at things, and we're just looking at the shapes here, so don't get too hung up on any of this other hybridization idea to pretend like you can't see that right now. But if we have 2 groups, 3, 4, 5, or 6, the base shape that it adopts is what we know. Okay, so linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral, that's the basic shape that it forms. But if we start looking at the number of bonding groups and the number of lone pairs, we see deviations from that, and we can get all sorts of other shapes, such as bent, trigonal pyramids, seesaw, T-shaped, square pyramids, square planar, all of that sort of thing. And so again, the electron geometry is just how many things are attached, the electron groups, whether they are bonding groups or lone pairs. The molecular geometry only considers the bonding groups within that original electron group specific shape. Don't worry, there's going to be plenty of practice of this.